Hi, my name is Tim. My teammates are Alex and Simon. We are Group 1. This is the video to demonstrate our weekly progress in terms of the final project. So far, we're able to make the BFlow 60 multiplier working on the FPGA board, and I just want to showcase that. So first, let's download the bit file. And then let's do a reset. For the first test case, I choose to do 1.1 times 1.1 just because it's simple. For 1.1, when you convert that to BFlow 16 format, it will be 3F8D. And then when you convert that back to decimal, it will be 16269. And then we do the same for B. And then let's check the results. As you can see here, the input are correct, the 3F8D, and then the output is 3F9B. And when you convert that to BFlow 16, it will be 1.21 as expected. And now let's do a different test case just to make sure it's not a fluke. So first let's do a reset. For this one, I choose to do 620 times 21.75. So for 620, when you convert that to BFlow 16 format, it will be 441B. And when you convert that back to the decimal, it will be 17435. And then for B, 21.75 will become 41AE in BFlow 16 format. And then when you convert that back to decimal, it will be 16814. And then let's see the results. As you can see, the result is 4653, which is when you convert that back to decimal, it will be 13485, which is the expected result. Let's just do one more to make sure this is not some fluke. So as usual, we should do a reset first. And then this time I choose to do 5.9 times 3.3. So for 5.9, it will be 40BD. And then we'll convert that back to decimal, it will be 16573. And then for B, 3.3, when you convert that to BFlow 16, it will be 4053. And then convert that back to decimal, it will be 16467. And then let's see the results. As you can see, the result is 419C, which is 19.5, which is the expected result.
Hi, this is Alex. So while Tim's been working on the actual implementation of our floating point units onto the FPGA, I've been working at the higher level trying to see what different designs would be best for our project. In Lab 10, we did BFloat 16. But we're designing everything from the ground up, so there's really no need for us to do that. Right now, what we've landed on is 5-bit exponent, 10-bit mantissa. And so, so we have multiple versions of the floating point units. This is the multiplier, there's the adder, and then the multiply accumulate just basically puts them together and pipelines them. And so I have this test bench here in Python that it generates random numbers, puts them in an input file, then compiles the Verilog test bench, runs it, and then writes to an output file. Then it reads that in, and it prints out the values and the expected and the error and all of that. So, okay, so we have about 0.85 error on the multiplier, 0.44 error, percent error on the adder, and 1.26% error on the multiply accumulate unit. So that's for BFloat 16, but with our new floating point module, these are just behavioral models. The workflow we kind of have right now is we design in behavioral, then we go and convert to structural, and that makes it a lot faster to synthesize. And it's also, we then have control of what our design is being synthesized into. Anyways, let's run this, and now you can see the error is down a lot already. So now this is 0.03%, 0.044%, and 0.1%. So just by changing how many bits in the exponent and mantissa, we've actually basically have a 10x improvement. That's about it for me. I want to cut to Simon. No more demo, but he's going to give some background on the block diagram that we're trying to implement right now. So the next step for us is to take this and actually get it working with our pipeline. So yeah.
As for the architecture diagram for encoding, so far is that we have our IMEM, which will have a custom ISA to use with this pipeline. We have our data mems, which are the scalar, random values, and the image inputs, or the batch inputs. So the first pixel across each of the images will be loaded into the batch, along with all of the scalar random values using our network processor, or like our network pipeline. So the scalars will remain the same across the whole set of, like, the first image will have the same scalar values applied across all of the pixels. So these will be updated for each pass through the batch. That gets passed into the FP multiply. That's where the equation that does the scalar times the pixel is done here in this stage. And then we accumulate after that. So that is the accumulation of the pixels that get done after they are multiplied against this scalar random value. It's not too complicated, and then that gets passed into the encoded data mem. And once this is all done, we have our entire first image complete and stored within data mem, and that would be passed out back out into our network processor.